This is video 1 for chapter 15 over equilibrium of our AP exam review. Let's go through a bunch of these multiple choice questions. So here we have a reaction. Actually, the next 5 questions refer just to this reaction here, so we'll be focusing on it. We have PCl5, which decomposes into these two gases. All 3 of these, notice, are gases. And a pure sample of PCl5 is placed in a rigid evacuated 1 liter container. Here it is. Here's the container. The initial pressure of the PCl5 is 1 atmosphere, so we get 1.0 atm. And we have nothing of the other products. So it's actually all reactant and no product to begin. The temperature then is held constant until we have equilibrium reached, and the figure below shows. So notice that at equilibrium we have all 3 of these gases present, because at equilibrium you don't finish the reaction. The reaction isn't finished, it just reaches a point of constant. So the total pressure being 1.4 shows us that equilibrium is different, the amounts are different than the initial amount. And remember, we have to lose reactant and gain product to get to equilibrium because we have nothing of the products to begin with. This doesn't mean 0, this means some amount. So at equilibrium, actually, we have less of this and a little of this, a little bit of this. That's kind of the picture that we see at equilibrium. All right, which of the following, number 2, let's go down and see if we can get some of these questions answered. So which of the following is most likely the cause for the increase in pressure observed in the container? And so they're asking us, why does the pressure increase? Well, we said we're forming products. A says a decrease in the strength of intermolecular attractions among the molecules. This is actually, intermolecular attractions is a physical reaction where we do have a chemical reaction going. So intermolecular attractions are actually not going to be the cause of the change. Intermolecular attractions are between molecules, physical changes, you can say. So those are out. We have an increase in the number of molecules, which increases the frequency of collisions with the walls of the container. We do have an increase of the number of molecules. We're increasing both these. Now we're increasing both these because the reaction shows we have twice as much or 2 times more gases as we have reactants. And that's why C would be the correct answer. 3 says, as the reaction progresses toward equilibrium, the rate of the forward reaction. So what happens is the rates equalize at equilibrium, recall. So the forward rate, though, decreases because we are losing reactant as we go toward equilibrium. So the forward rate should decrease. The reverse rate, because this is now an equilibrium system, the forward rate decreases, the reverse rate increases until they become the same, and that's the whole point. So C is the correct answer. The forward rate decreases and becomes a constant non-zero rate at equilibrium. So the definition of equilibrium is the point at which forward and reverse rates equal. Forward rate equals reverse rate. Reverse rate. Good. Take a look at number 3 rather than number 4. We skip number 1, possibly. There is no number 1. So 4 says, if the decomposition reaction were to go to completion, the total pressure in the container would be. If you take a look, since we began with 1.0 and we have 2 moles of products, then we should double that and have 2.0. That's the idea. The 2.0 should have been the product if all the 1.0 disappeared, since we have 1 mole of gas on the left and 2 moles of gas on the right. 5 says, which of the following statements about Kp, the equilibrium constant for the reaction, is correct? Now let's go ahead and do a quick little, I'm going to go up and do a quick little icebox. And we encourage you definitely to do iceboxes with equilibrium. So they're asking for the Kp, the value of Kp, whether it's going to be smaller or greater than 1. Now, because we're beginning at 1, if we set up the icebox like so, this would be ICE. Remember, the icebox keeps track of the reaction progress. So we'll say we have 1 at the beginning here, nothing here. As we get to equilibrium, we have to lose from the reactant and gain the products. So at equilibrium, we have x, x, and then 1 minus x. Now they tell us that the total pressure is 1.4 at equilibrium. So all these gases combined together will give you a total pressure of 1.4 because each gas is contributing individually to the total pressure. So 1.4 will equal this gas plus this gas plus this gas. This is different than products over reactants. K would be products over reactants. And we'll have to plug it into K in a minute. But here, the reaction that we're setting up is actually, we're adding these pressures. So 1 minus X plus X plus X. I take a second to see what I'm doing here, because these together are the pressures. So solve for this. Minus X and X are out. So we have 1.4 is 1 minus X, plus X part. And then we subtract 1, so 0.4 equals X. Now because X is one of these, I can actually plug in 0.4 into products over reactants. It'll be X times X divided by 1 minus X. So I have myself 0.4 times 0.4 divided by 1 minus X. 1 minus 0.4 is 0.6. So here's what we have. Now we can probably compute this without a calculator. If I switch this over once, that's 4 times 4, which is 16. And then I switch it back twice. I got 0.16. Divided by 0.6. 0.6 is 6/10. So it's like multiplying by the reciprocal, so times 10 over 6. 16 times 10 is 1.6, so I got 1.6 over 6. I can see that this answer will be less than 1. Can you see that it'll be less than 1? It'll probably be something like 0.2 something, 0.2, I don't know, 8 or something. That's getting a bit tight. But can you see that it's going to be less than 1? So we can actually do a quick little calculation. Now, if you were not comfortable with the calculation, you can probably still guess that Kp must be less than 1, because the amount of products we formed isn't that much. We only formed 0.4 as compared to the starting reactants. So we didn't produce a lot, and then K is products or reactants, which means we don't have a lot of products, which means this top number is small. We still have a lot of reactants. So the number is going to be a small number divided by a big number. We'll still get a small number. So think of it that way. So think of it logically. I wanted to show you the actual calculations so that we could use them a little later as well. 6 says additional Cl2 is injected into the system at equilibrium. Now Cl2, if you take a look, is actually a product. So which of the following graphs best shows the rate of the reverse reaction as a function of time? Because Cl2 is a product, as you increase Cl2, the system will try to decrease Cl2 and move the reaction to the left. Now, which of these matches? It turns out B is the best answer, because as Cl2 is added, you suddenly increase in pressure, and then you slowly decrease until you become constant again. But you will attain a value that's above the initial. You'll never get all of it taken away. In fact, this graph is wrong because it shows the increase initially, but then the equilibrium is reached and you have less Cl2 than you began with. That's not right. You'll actually have more than what you began with, except it'll reach a number higher. And then these two are out because you suddenly increase. These make no sense. So think through these. Now let me do a few more down below. Let's actually take a look at number 13. Let's do number 10, and then we'll do number 13. So here, for number 10, we have a reaction. We have 4 moles of X and Y are placed in a 1 liter vessel. So we have 2 moles here, 2 moles here, and allowed to react at constant temperature. According to the equation above, 6 moles of Z is produced. What's the value of the equilibrium constant Kc? Let's quickly set up an icebox. This is actually what you were supposed to do for this one. Set up a quick icebox. So it looks like we have 4 of each of these. So we have a 4 here, we have a 4 here. This is a 0 to begin. Now we're told that at equilibrium we got 6 moles of Z, which means this number is 6. So take a look. This would be the setup of the icebox. And they're asking us for Kp. We can fill these in since we know that we should have gained plus 6 here. Now here we lost half as much, because for every 2Z we have 1 Y. So we minus 3, minus 3. These become 1. This makes it easy. So our K should be 6 squared, because of this 2, divided by 1, which is 36. And that is how we got E. I did that one very quickly. Take a look at it and then find some questions like it. Incidentally, number 9, let me mention number 9 real quick. We can manipulate the equilibrium constant by changing the reaction. So here we have equilibrium constant is 95. What's the value of the equilibrium constant for the following reaction? So notice for this reaction, what we've done is we flipped it. Oxygen was on the right, now it's on the left. N2O5 was on the left, now it's on the right. And we've doubled it. Notice we had 2 NO2, now we have 4. We had 1 N2O5, now we have 2. So when you double the coefficients, you square your power. Because remember, the coefficients go into the power of the equilibrium constant. So you'd square that. And then if you flip the reaction, because K is products over reactants, your products become reactants, your reactants become products, and you invert the number. So what we're going to do, we're going to invert 95, which is here. We're inverting 95, and then we're going to square it. So this would be the answer. So know how to manipulate the equilibrium constant, just in case this comes up. And then lastly, make sure you can do some Le Chatelier principle problems. So let's take a look at number 13. So Le Chatelier was pretty prominently featured in the equation. And actually in the first example, on the first page, we saw Le Chatelier principle with the increase of Cl2 gas. So here we have, consider the following reaction in equilibrium. Here we have a reaction. And we notice that it's exothermic, so heat can be thought of as a product. This is the way to think of it. Anytime you have exothermic reaction, heat is a product. So Le Chatelier principle predicts that equilibrium partial pressure of CO2 can be maximized. We want to maximize CO2, which is a product. We want to increase. So we want to shift the reaction to the right. So what should we run the reaction at? Now, let's take a look. Temperature and pressure are the two things that are changing here. So we have temperature and we have pressure. Now, if you increase the temperature, this would be like adding heat. So if we add heat, this would be like adding product, because heat is a product, since it's exothermic. The shift will go to the left to remove. Remember, Le Chatelier says the system will do the opposite of what you've done to it in order to get back to equilibrium, because you've upset its equilibrium. So as the system shifts left to remove the added heat, you'll actually reduce CO2. So we don't want to increase heat, we actually want to reduce heat. So if we do the opposite, if we reduce heat, if I remove the heat, then the system, if I cool the system down, then it'll go right to replenish that heat, because heat, again, is a product. So we want to do this at low temperature. So high temperature's out. And let's think about pressure. Now, if you take a look, we have more gas on the right side. We have 2 plus 1. We have 3 moles of gas on the right side of the equation. We only have 2 moles of gas on the left side of the equation. So we have more pressure on the right. If you increase the pressure, the system will try to decrease the pressure. Now, the way it does it is by moving to the side with less moles, because moles of gas cause pressure. So it'll go left to reduce the pressure, removing with it CO. So in fact, what you want to do is you want to use a low pressure. If you do a low pressure, which means you've reduced the pressure, the system goes to the right to increase that pressure, since you have more moles on the right, increasing CO. So we want to do this at low pressure. So you want low temperature and we want low pressure. This is the answer. Incidentally, E is out because carbon, solid carbon, well, this makes no sense because there's no carbon in the reaction. But if you were to have a solid in the reaction, remember that solids do not affect equilibrium. So you can remove a solid. Say if you did have solid carbon for some reason, you can remove a solid, you can increase the solid, and there'll be no change in equilibrium. As long as the carbon being removed or added doesn't change the volume of the system, because another way to reduce or increase pressure is by increasing the volume. So you could have lowered the pressure, for example, by increasing the volume. So as long as the volume isn't affected by the removal of the solid, then you'll be all right. Okay, so think through those questions and do all the rest, and we'll see you in class.